Good morning, students. In the last class, we discussed about one of the periodic property of the elements, that is atomic radii. Okay. So in that atomic radii, we studied covalent, different types of atomic radii, that is covalent, metallic, van der Waals, and ionic. Okay. So in that, what we know, covalent radius means it is the half of the distance between, or half of the distance between of the length of the bond. Okay. So covalent bond length is there, like x is there, then x by 2 is the radii, that is covalent radius of the respective atom. Understand? Half of the distance of the covalent bond, or half of the length of the covalent bond. Okay. Next one is metallic radius. Metals means they are in solid state, they are arranged in adjacent to each other. So the force of attraction between two nuclei is a metallic bond. So half of the distance between two nuclei of adjacent atom are called as what? Metallic radius. Okay. So van der Waals means they are in absorbing gaseous states. In gaseous states, the atoms are not adjacent to each other, but they are neighbor to each other. Okay. So then it is the half of the distance of the half of the distance between the nuclei of neighboring atoms, not adjacent. Okay. So if adjacent atom, that is metallic. If neighboring atom, van der Waals. If the bond length is there in that term, means that is covalent bond. Ionic means that is the distance between the nuclei of the opposite charge. As the cationic charge increases, like -1, -2, -3, then the size also increases. Understand? So next one is, students, the important property, another one, that is ionization energy. Ionization energy. It is also a very important topic. Okay. So based on this, they'll ask question for 2 marks. Okay. Which are those questions? I'll explain. Sorry, 3 marks. Which are those questions? I'll explain. Understand? So first one is, what is ionization energy? Ionize means what? Formation of ions, whether a cation or an anion. But here, always the ionization refers to remove of electron. So what is ionization energy? Means the amount of energy required to remove an outermost electron from isolated gaseous atom. The amount of energy required to required to remove an outermost electron from isolated gaseous atom. Simply we are taking them as a gaseous atom. We can remove the electron from sodium also, means sodium also exhibits some amount of ionization energy. Okay, why we are considering gaseous atom means because at the end of the periodic table, noble gases are there, all are gases, and they have a stable configuration. To break their stability, we require more energy. Understand? That's why this is the definition they given. The amount of energy required. So required means what? Always the energy is added to the molecules to remove electrons. Understand? So always this ionization energy is positive. Okay, and it is measured in kilojoules per plus, that is kilojoules per mole. Understand? Next, so students here, for example, I will take metal M. Okay, if metal M is there, assume its atomic number is still it is 0. Oxidation state is 0, equal number of protons are there, equal number of electrons are there. Okay, so when we remove an electron, it forms M plus 1 plus electron. Okay, this is first ionization energy. The energy required to remove a first electron from the neutral atom. Neutral atom means the charge is zero. There is no plus charge, there is no minus charge. Okay, so the amount of energy required to remove electron from a neutral atom is a first ionization energy. Next, consider this. M plus 1 is there. If you want to remove another one electron means that is N plus 2 plus electron. This is IE2. Okay. Similarly, we can remove, so M N minus 1 by N plus N. Okay. So N plus 1 means N is equal to 2 if we take means 2 minus 1 means 1. So N of N minus 1 gives rise to M plus N plus N electrons. Or here we are considering N minus 1 is only 1 electron. So then it is IEN. So the removal of first electron is IE1, removal of second electron is IE2, similarly removal of N electron is IEN. Understand? So here students, always the ionization energy trend follows. IE1 is there, IE2 is there, IE3, etc. IEN. Okay? So listen, here, if the metal atom is there, it is neutral instead. After removal of electron, it changes to plus 1. That is, it changes to cation. So when it changes from atom to ion, it forms what? Cation means the size decreases. Understand? So from atom to ion, which ion? Positive ion, that is cation. You know the cationic size is always less compared to these atoms. Okay? In the last class I wrote this cationic size, cationic radii or a size is always less than atomic radii. Correct? So here, from year to year, the size of this is less. Here, as I told you, as the number of positive state increases or a positive value increases, again size decreases. Okay? So M1 is greater in size compared to M plus 2. So it is greater in size compared to M plus N. If the positive charge increases, size keep on decreases. Understand? So that means what? If size is less, okay, here nucleus is there, okay, here shells are there. Understand? If size is less means they become very close to nucleus. If size decreases means here initially size is here, later size becomes here, later here. Then what happens? When the size decreases, they come closer to the nucleus. When they come closer to the nucleus, the effective nuclear charge increases. Understand? When they comes closer to the nucleus, effective nuclear charge increases, which is very strong. So that's why we require more energy to break the bond. So always, if the size is less, energy required is more. If the size is more, energy required is less. Understand? For example, a chalk piece is there, you assume. If complete a big chalk piece is there, if we want to break that, we can easily break. We don't need to apply extra energy for that. If small chalk piece is there, we have to apply more energy. Correct? That is the way. If the bond size is more, energy required is less. Understand? Next, if the size is less, energy required is more. Like that. Assume this is the chalk piece. To break this, we require less amount of energy. So assume only this much of chalk piece is there. So we require more energy to break this chalk piece. That is, this is more size, this is less size. If less size is there, then it requires what? More energy. Okay. So here, always the energy required IE1 is always greater. IE2 always greater than IE1. IE3 always greater than IE2. Similarly, IEN is greater than IE3 at a respective top model. Understood? Okay. So this is the trend. Actual trend, this one. But it varies in the periodic table. Understand how it varies, what happens, what is the reason for that, I'll explain. Okay. Remember this one, if the positive charge increases, then the size decreases. then ionization energy increases. If size is less, energy is more. Okay. Next, if you want to explain it in the periodic table. So in the last class we discussed along the period, what happens to the size? Okay. So from here, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So as we move from left to right along the period, size decreases. Correct? Because the electrons added to the same subshell increases effective nuclear charge. Means here 1s1, sorry, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. The electrons enters into the same subshell. That means size increases. Sorry, size decreases. Okay. Next here you consider lithium, sodium, potassium, rubidium, cesium. If you consider here, this is 2s1, this is 3s1, 4s1, 5s1, 6s1. Here extra shell is going to add. So then here size increases. Okay students? So for ionization energy, as I told you, if the size is less, energy is more. If size is more, energy is less. Then what happens? So along the period, okay, ionization energy increases because size decreases. Understand? And along the group, ionization energy decreases because size increases. Understand? You can say two reasons. Why along the period the size, why along the period ionization energy increases means because size decreases. They are inversely proportional. Next, another one, along the period, effective nuclear charge is also increases. Effective nuclear charge is more, ionization energy is more. Effective nuclear charge is less, energy is less. Okay, so here how this effective nuclear charge affects this? Listen, this is 1s then 2s, 3s, 4s, 5s. As the number of shells increases, they are moving far away from the nucleus. So force obviously decreases. Okay, so here the electron enters into the same subshell. That means the force of attraction increases, results in decrease in size. They are nearer to the nucleus means the size increases. They are far away from the nucleus means size. The nearer to the nucleus means effective nuclear charge increases. Far away from the nucleus means effective nuclear charge decreases. Okay, distance is more, force is less. That is the thing. So this is what the trends in the periodic table. Okay, but the trends in lithium, beryllium, boron, and nitrogen and oxygen, it follows a different manner. Understand? So if you want to write the increasing order, decreasing order of this ionization energy means it will be like this. Correct? It will be like this. But this is the wrong. This one is wrong. Why? Because before beryllium, before nitrogen, oxygen comes first. Before beryllium, boron comes first. Understand? The trend is lithium, boron, beryllium, carbon, oxygen, nitrogen, fluorine, neon. This is the correct trend. Understand? Why? What happens here in the between beryllium and boron, oxygen and nitrogen, they are going to ask you for 3 marks question. How the second ionization energy or first ionization energy of the respective element is different. Or you may ask why the first ionization energy of boron is less compared to beryllium, even though it is in a greater atomic number. 2s to 2p1 is there. According to the trend, so along the periods, if ionization energy increases means this should have greater ionization energy. But instead of boron here, beryllium has greater ionization energy. What is the reason for it? Okay, alright? Then you think. So students here, remember one thing, for s orbital, we can fill maximum 2 electrons. Correct? So for s orbital, we are considering only one box. This is magnetic quantum number. So in the atomic structure chapter, I will explain. Just remember this one. For s orbital, 2 electrons can fill, so only one. For p orbital, how many electrons can fill? 6 electrons means you require 3 OH. Okay. Next, d orbital means maximum electrons to be filled is 10. That is 1, 2, 3, 4, 5. Okay. Next, f orbital maximum electrons to be filled is 14. So 1, 2, 3, 4, 5, 6, 7. As if how many number of electrons are there divided by 2 number of orbitals will be there. This is the s orbital, p orbital, d orbital, and f orbital. Understand? So remember this one. So here lithium is there, beryllium, boron. Okay, I'll explain only. Okay, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Neon we didn't consider because as we know they consist of a stable configuration. Completely filled configuration is they require high energy. So students here, if you take atomic number, here it is 3, 4, 5, 6, 7, 8, 9. Correct? Next, if you take electronic configuration, this is 1s2, 2s1. So 1s2 I will leave students, just I write 2s2, 2s2, 2p1, 3s2, 3p. So 2s2, 2p2, 2s2, 2p3, 2s2, 2p4, 2s2, 2p5. Here neon if I take, that is 10, 2s2, 2p6. Okay. So here, if we take a box diagram means that one, right? Only for s orbital is there means only s. Here also s orbital is there means only one box. Here s and p means 1, 3. Here also sp means 1. All the side, right? Like this. Understand, students? Okay. Now try to arrange our electrons in this box. So initially only one electron means it is in this box. Here 2 electron means one is in this direction, another one is in this direction. This is the way to filling up of electron takes place. Okay. Next, this one is 2s2 completely filled. As I told you, maximum electrons is 2 only. Here only one is there, 1. Next here, 1. Next here, students, here 1, here. So that means what? Because all the p orbitals are having a same energy. Okay. So initially, each and every orbital should fill up takes place first, then pairing up takes place. If all the orbitals are singly filled, then only pairing up takes place. I'll write, then you came to know. So here it is 1, 2, 3. Okay. Next, here 2 electrons, 1, 2, 3. Again pairing up. Okay. Next here 2 electrons. This. And here all are paired up. Remember students, if the orbital is singly filled or completely filled, this is stable. Half filled or completely filled. Understand? Somewhat stable configuration is there. This is 2s2 compared to this 2s2 2p1. Understand, students? So this is a completely filled configuration. This is a stable, this is an unstable configuration. If it loses one electron easily, then it attains a stable configuration. Understand? So in the configuration, 2p1 is there. If we remove that electron easily, So listen here. Lithium means why it loses one electron? Because if it loses one electron, it attains noble gas configuration, stable configuration. That way it easily gives one electron. Understand? So it requires very less energy. Then here and here. So here it is a stable configuration. We have to break stability. Then we require more energy. But here it is unstable. If you remove this electron, it becomes stable. That means it easily donate an electron. That's why in boron and beryllium, boron has less ionization energy than beryllium. Because in the boron, the electron is removed from the unstable configuration, and in beryllium, the electron is removed from the stable configuration. Understand? Similarly, the same trend follows in oxygen and nitrogen. Listen. Here it is oxygen, here it is nitrogen. In nitrogen, completely filled and half filled is there, that is stable. The electron should be removed from this p orbital. One electron, the last electron should be removed from this orbital. Means we have to break stability. Understand? If here oxygen is there, already one electron is extra present here. Okay? If we remove one electron, it attains a stable configuration. Understand? So to attain stable configuration, it easily loses one electron. So it requires very less energy. It already prefers a loss of electron. Understand? So that's why to become stable, it easily donate electron if you apply a less amount of energy. But here it is already stable. To break that stable molecule, we require high energy. Understood? So that's why the ionization energy of oxygen is less compared to nitrogen. Because nitrogen has a stable configuration of 2s to 2p3 and oxygen has unstable configuration as 2s to 2p4. Okay. Similarly, these are completely filled configuration means they are highly stable. They require very high energy to break the molecules. Understand? So this is how this trend follows. Okay, very very important. And everything depends upon what? The ionization, so the electronic configuration. The thing they will ask students, the first ionization energy of boron is less, beryllium is more. Why? Because boron has an unstable configuration or beryllium has a completely filled configuration, so it is stable. We require more energy to break the stability. If you write this much, you will get 2 marks. It is a 2 marks question. Okay, either they will ask from nitrogen and oxygen. So you have to write nitrogen has a stable half-filled configuration, oxygen has an unstable configuration. To break the stability, nitrogen requires more energy, so this oxygen requires less energy. Understand? So if you write this much, you will get complete marks. Only in between beryllium, boron and oxygen and nitrogen they will ask. Okay, this is what? The first ionization energy, removal of one electron. Understood? Okay. This idea. And remove this box diagram. So students, after first ionization energy, the configuration becomes, if you remove one electron, it is only 1s2. After first ionization energy means we remove one electron. Okay, m+1 state. Okay, here it becomes 2s1. Here it becomes 2s2. Here 2s2 2p1. Here it is 2s2 2p. Next 2s2 2p. Next 2s2 2p. Here we cannot remove easily. Assume this one. So students, here after removal of one electron, this one becomes stable, and this one becomes stable, and this one becomes stable. If you write a box diagram, it is a completely filled configuration. This is also completely filled, and this one is with the p orbital off filled. Correct? And remaining are incompletely filled orbital. So students, here the beryllium as initially at the second ionization energy, here lithium and beryllium you consider. Okay, here beryllium has 2s1 configuration, this one is 1s2 configuration, then which one requires more energy? Here 2s1 is there, here 1s2 is there. Understand? This one is like 1s2, 2s1. Which one is stable here? Which configuration is stable here? 1s2 configuration stable because it is completely filled configuration. Here 1s2, 2s1 is there. 2s1 is unstable. Understand? Comparatively unstable. If it easily loses an electron, then it attains noble gas configuration. Then the second ionization energy, the beryllium is less, lithium is more. Understand? So in the trend, students, we can easily say along the period ionization energy increases, along the group ionization energy decreases. But when we compare the ions, understand? When we compare the ions, the ionization energy depends on stability of the configuration. Okay, so lithium and beryllium is that along the period ionization energy increases means beryllium should have greater ionization energy. But here what happens? Lithium has greater ionization energy for second ionization energy, IE2, to remove 2 electrons from the atom. Understand? If you want to remove 2 electrons, this one requires more energy than this. Similarly here, oxygen and nitrogen. So after removal of 1 electron, nitrogen becomes unstable configuration, oxygen becomes stable configuration. So second ionization energy is more for oxygen than for nitrogen. Understand? Similarly for third, fourth, fifth, you can by comparing with the reactions. So listen, third ionization energy if you consider means this carbon becomes stable. Understand? Third ionization energy means this carbon becomes stable rather than this. Okay, that is the way to consider the ionization energies. Understood? Anything doubt in this? So this is all about the ionization energy. What is ionization energy? Means the amount of energy required to remove the outermost electron from isolated gaseous atom. Okay, so if I write the graph, students, ionization energy versus atomic number of first period elements. Right here. This is ionization energy in kilojoules per mole. This is atomic number. Here I take lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So like 3, 4, 5, 6, 7, 8. Then I take the energies like that is 500, 1000, 1500, 2000 and 2500. Okay. Next year, when lithium is there, here it is. So its energy is nearly 500. This one. Okay. This is 520. Next, beryllium is there. Its energy is 899. Okay. And next, boron is 800. And here, boron, that is 800. Next again, carbon, students, that is 1086. That is carbon, and take 1086. Next, this nitrogen, nearly 1500. Okay, and this carbon is, oxygen is 1300. 1600. And this neon, that is 2000. So if you draw the graph, so initially it increases, again decreases, again increases, then decreases, and again increases. So students, compare here. As I told you, listen. I write lithium less than boron, beryllium, carbon, nitrogen, oxygen, fluorine, neon. This is the trend I told. So listen. Lithium has less energy than boron. Here it is. But here compare it. Beryllium has more energy than boron. Beryllium has more energy than boron. So energy increases up to beryllium, decreases for boron, again increases up to carbon, increases up to nitrogen, decreases for oxygen, again increases up to what? That neon configuration. Understand? That means this beryllium and nitrogen has more ionization energy than this boron and oxygen. Configuration, they have unstable configuration. This is the graph that tells about what? The increase in the ionization energy. Understand? So this is along the period, students. If you consider along the group, consider along the group. That is ionization energy in kilojoules per mole. Okay, here it is 350, 400, 450, 500, 550. Okay, next this one is the lithium atomic number 10, 20, 30, 40, 50. And last one is 60. Okay, so students, lithium atomic number is 3. Okay, it has high ionization energy. If you go along the group, ionization energy decreases. So lithium atomic number is 3. It has the ionization energy here. This one is what? Lithium. Next one is sodium. Sodium atomic number is 23 in Cl. Right? Sodium atomic number is 23. Here I am writing 23 means here it is. Okay. Next, potassium atomic number is sodium atomic number is 11. And potassium atomic number is 19. Correct? Atomic number we have to consider. This one is 3, sodium is 11, this potassium is 19. Okay? And here it is 419 energy. Next one is rubidium. Rubidium atomic number is 34. That is here. Potassium, rubidium. This one is cesium. Atomic number is 56. 55. So students, here, if you consider, this is the, here what happens? For lithium, here lithium is there, sodium is there, potassium is there, rubidium is there, cesium is there. So here it is lithium, boron, beryllium, boron, carbon, nitrogen, oxygen, fluorine here. So if we consider from this lithium to neon, obviously we didn't consider the variation in the middle of the graph means. So from year to year, the energy increases from lithium to neon. We are not considering this one. Variations we are not considering, just we are considering what? Graph. From lithium to neon, the ionization energy increases. That means along the period, ionization energy increases. From here, lithium to cesium means along the group, ionization energy from year to year means decreases. Understand? So this graph tells about the variation in the ionization energy in the periodic table. So students, you have to remember what is ionization energy. Means the amount of energy required to remove an electron from an outermost shell, or you may say outermost electron from the isolated gaseous atom. And another one, along the period, this ionization energy increases because size decreases. Understand? Next, along the group, the ionization energy decreases because size increases. Another one reason for increase in ionization energy means if the size decreases, effective nuclear charge increases. If charge is more, means force is more, nuclear force, then we require more energy. If effective nuclear charge is more, energy required is also more. Okay? If effective nuclear charge is less, energy required is also less. Okay? This thing you have to thorough. Okay? Always, whenever there is, you should remember this one. Okay? Another one you have to remember the difference between these two. That is important for 2 marks. The reason for the high ionization energy of nitrogen and oxygen, what is the reason? Why the nitrogen has more ionization energy means? Because it has a stable configuration than oxygen. Oxygen has unstable configuration, nitrogen has stable configuration. To break stability, we require more energy. Okay, I write this because it is important. So I'll write it on. Okay, write the question first. The first ionization energy of boron is less than beryllium. Give reason. Okay. Next, second, same. The first ionization energy of nitrogen is more than oxygen. Give reason. Either them has increase in energy or them has decrease in energy. Okay? The thing you have to write what? Because the first ionization energy of boron is less because it has an unstable configuration of 2s2 2p1. Okay. Next, beryllium has a stable configuration 1s2 2s2. To break the stability, we require more energy. Only this much. Next, in nitrogen. So the first ionization energy of nitrogen is more because it has a configuration 1s2 2s2 2p3. Stable configuration. Next, oxygen has unstable configuration 1s2 2s2 2p4. Okay, to break the stability in nitrogen, we require more energy. Understood? Only this much you will get a, because often they used to ask these questions. Only this. Okay, so in the remaining properties I will explain in the next class.